I dressed up as myself today.
I dress up as myself.
They knew what they were doing. Yeah. All right.
We're enjoying the updates from your exam.
From the exam, yeah. Yeah.
You
No,
look surprised.
yeah.
Took a picture of you.
uh, Timothy, right? Son of a bitch.
I haven't seen Tim today. I just saw you teaching Theo.
Yeah, I know, right? And then I liked how you threw in immediately because the homework's due later, right? Because he was acting like me.
He
Yeah.
caved immediately.
Yeah.
Immediately,
there
damn
was
right.
no
No pushback at all, right? Good for him. I thought that was.
So actually, thanks, Mike.
You're welcome. Yeah, my wife participated. My wife gave him everything. And my shoes, my pants, my favorite shirt, and then one of my favorite flannels. This is bullshit. And my wife put it in a nice little package for him and left it on the front porch for him. I didn't know I was gonna pull off the beard because he can't grow a beard. That's a true statement. He himself can't grow one, and so it's like, well, how's he gonna do this? And then he found a way. He found a way. He painted it on. So who wants to do the tour of the session? Oh, we got two people saying yes. 3, 4, 4 total. 4 total. So what we might do, if you don't mind, we'll just jump in with the structure. Can you do it at 1?
I would
Yeah.
see. I would show up at 1.
You would show up. What you can show up at 1 if you want.
That's when solids get out.
Just
Yeah.
remember really.
Talk it down at 1250, right?
Yeah.
Yeah. If there's only like 4 of you, let's just do that. Let's just jump in with the structure. Then Axel doesn't have to give 2 tours. He can just give 1 tour.
And I can get.
Giaforte Hall, Tony. Axel offered it because I know that they're doing it for structures 1 today. I said 2, but it's structures 1. And so then, so let's plan at 1 then. We'll kind of jump in with him. Hey Kyle, how's it going?
Good. How are you guys?
Good. Good. Happy Halloween.
Yeah. Happy Halloween. Are you dressed up?
I'm not dressed up. Tim dressed up as me though.
I was gonna say, did you dress up as your favorite professor yourself?
Tim dressed up as me, and then he all the way down to my shoes. The same shoes that you wear, Kyle. Same ones. He went all the way down to the same shoes and pants. My wife gave him everything that I own, and so he wore everything except for his underwear. Did
you ask?
I did. I had to go get my underwear on because that'd be really creepy. He did not have my underwear. So
Did he dye his beard white?
well, he doesn't. He can't grow a beard himself. Probably similar to you, Kyle.
Yeah, it's a problem. Yeah.
And so then he drew a beard on his face. I'll send you a picture here shortly.
Awesome.
Cool. There's more donuts up here, and then candy if anybody wants it. Should I send the candy around? Trick or treating. Trick or treating. All right, you're up, Kyle.
Alrighty. Let me get my screens situated. Alrighty. Okay, so we're picking back up on this presentation that was, 12 steps that you follow in design. And this is, as I mentioned to you guys, this is a presentation that we're getting ready to give to a lot of structural engineers associations across the nation and do some webinars on it. So it very much is a real world presentation, just like you'd be doing kind of out when you get into the real world. I'll also say, just to build a little confidence in you guys, I used to manage a pretty large engineering department And we had a couple hundred engineers, and I hired engineers from all throughout the US, all the big name universities and stuff. And I'll still say Montana State University engineers had an edge on most others from the standpoint of MSU's a little more code oriented and real world oriented. First, a lot of these other universities are more theoretical. They don't really get into the half of these guys graduate and they've never even opened up a code book or looked at one. They have master's degrees in engineering. So you guys should have some confidence as you walk out of MSU when you guys start applying for jobs. But just a little side note. Okay, so we talked a lot about restraint shortening in the last hour. And at the end of the day, the summary was the one take home: concrete's going to move 3/4 of an inch per 100 feet of unrestrained length. You have to design for it. And only about 20% of that's going to be coming from the effects of post tensioning. That's some elastic shortening and some creep on there. And that's the most overlooked thing in post tensioning. And most amount of litigations, lawsuits that happen within elevated concrete that's post tension come from lack of proper attention to that restraint to shortening. So if you're to spend the majority of your man hours that you have budgeted on anything, I'd spend it more on the restraint to shortening than I would even the calculations for service level and all that, because again, the software is going to do that for you. You just need to know what's going on behind the scenes. So after we figured out that restraint to shortening, now we're going to drop into, let's figure out our tendon configuration. And we've seen this slide. We talked about it. Just a refresher. Back in the day, they did the uniform basket weave, which is the far left picture. Then at some point, they banded all the tendons together in the 70s in a single direction. And that made life a lot easier in the field. Your calculations are still exactly the same, because when you look at your tributary width, it doesn't matter. You know, when you're running a calc, you don't care where a piece of rebar is left or right in your slab, right? Or your beam. Just like a PT tendon, you don't care where it is left to right. And so banding it together from a flexural capacity standpoint, things don't really change. And then banding it together in two directions, now that's exactly the same as doing it in one direction. You're just doing it both ways. And the idea behind that is to be able to do slab openings. And with lots of office buildings, you're coming back and you're retrofitting over the years. One tenant might come in, they want 2 levels of the tower, and so they're going to put a stair opening in there. Or hospitals are always punching holes through the slabs. So the idea of doing a banded tendon distribution is you can come back and you can cut into the slab later. Because remember, with an unbonded post-tensioning system, if you ever cut in and hit one of those unbonded tendons, the thing's unbonded. You're gonna lose all your force in that tendon. With a bonded pre-stressing, you don't. You just redevelop that transfer length. It starts over again. And so this helps you come back and retrofit slabs. And it's also gonna be way more efficient doing that banded for the installation out in the field. Here's an example of a non-traditional tendon configuration layout, which was pretty similar to banded. This was 55 Hudson Yards. It was a high-rise tower in New York City, and it was going to be an office building. And you can see that they did a tendon distribution that was non-banded uniform, and they had to get through the building code. They had quite a bit of mild steel in there, and you can see the areas of green on the right. Those are areas that they can come back and they can saw cut openings in the slab. And then the areas in white, those are areas where they can come back and they can do smaller openings in there. So it's been done before. And it's also been done on a few projects down in Florida where they did banded tendon distribution. And they just had to do, they had to reinforce it more like a two-way slab for the minimums because the building code hadn't accepted this yet. It's done in Europe all the time with a lot of steel. So it's not a new concept. It's just new to the US of doing this banded. What's new to the world is doing banded with really no rebar in there. So when we say, how is it code accepted? There's a brand new building code out there, and that's called ACI PTI 3/2025, 25 being the year that it came out. And this one is for post-tension structures. The precast guys have one that's called ACI 31819. And then, of course, you guys know what ACI 31818 is, right? Or 318 is on there. And so in this year's 31825, there's a section that says you can design post-tension structures to this brand new building code that just came out, which is ACI PTI Joint Code 320 on there. And in that building code is where it'll tell you that you can do a two-way or a dual banded slab configuration and layout for it. This code, the reason why they did this code was to be able to move things through quicker and keep doing updates. They're going to update every single year. 318 does a new update. They're going to just match it. So you always have the same version coming out. But they wanted to separate themselves a little bit from 318 just so that they didn't get so caught up in the politics of taking forever to get code provisions passed. So they went to 318 and simply said, just allow us to state everything you need for PT, and 318 said that. If you really want to dive more into this dual banded layout, and this is more for the folks who've been doing PT a lot and they're kind of skeptical of it, there's an ACI journal article out there. There's a PTI technical note out there. And that technical note, back when I was in grad school in this class, my professional paper was on doing this exact layout. And so we more or less based that tech note. We took my professional paper and ran with it on that. And so there's quite a bit of information out there on the studies. We also went to Virginia Tech and did some full-scale test or partial-scale testing of these slabs. We did at third scale, and we did a banded tendon distribution in each direction. We did a banded uniform tendon distribution. We looked at the results. The group that sponsored this slab, they do steel fibers in concrete as an admixture. And those steel fibers, they kind of look like hairpins that you have, and you can put them in your concrete just as an admixture, and it makes your concrete more ductile. You can get more plastic section properties out of your concrete. And they did it because their intent and where they want to go with this is they want to say, we don't want to put in any rebar, we don't want to put in any stud rails, we just want to add these hairpin looking things, this steel fiber reinforcement to our concrete, pour that concrete slab. So you just have the PT tendons, a little bit of rebar just to support the elevation of the PT tendons, and no top steel, no minimums, no punching shear, stud rails, anything in that. It'll all just be that fiber reinforcement. So they're the group that paid for all this testing. When you looked at the results, what we saw with the banded, both analytically and with the actual testing, was it performed better than the banded uniform distribution did, ever so slightly. And one of the reasons for that is it's a little counterintuitive, but your max bending moments, which also means your max bending stresses, they occur along your column lines and not necessarily mid-span. Intuitively, you'd think that middle area of the slab, you're going to see your max positive flexion there, but it's really happening when you look at plate bending, continuous plate bending model, it's really happening along your column lines. So what you're doing is you're concentrating those uplift forces, those balancing forces that we talked about along the column line, where you have your max demand moment. And so because of that, that's why we're really seeing increased, more favorable behavior with that banded tendon distribution. We did say, though, that, hey, we do need some sort of minimum amount of steel in there in case there's ever extreme overload. Say there's a giant point load put down on that slab that wasn't accounted for in design, or some sort of ductility, or just to get the world to buy off on it. So we said you need to put in some minimum amount of bottom steel out there. And that minimum amount is 0.001 area gross. And that really comes out to be, for 8-inch thick slab, just number 4 is at 24 inches each way. So it's not much steel. It's a very light mat of steel that's put in there. It really, in my opinion, helps more with that early shrinkage crack control, especially before you get the pre-compression on that slab. But it's essentially nothing. It's not doing anything in our calculations. You can count it for your positive flexure, but you don't need it. If you looked at it, you got plenty of PT tendons in there. So it's a little bit of warm and fuzzy steel is all that is. We talked about this in the previous presentations, but remember, lay out those tendons. So now that we understand the restraint to shortening, now we're going to go in and we're going to start laying out where do we need to put these tendons. We're going to do banded uniform one direction, flip it, and then we might even lay out banded and study all 3 options and figure out what makes the most sense for this particular project. Do that in PDF. Spend those couple hours of upfront work. That's going to easily save you 10 to 20 man hours downstream of running your actual FEA models by doing this step up front. So you're just going to go through, do exactly what I just said there. And remember, 125 PSI is your minimum, 300 is your max that you can do. And that's your tributary area at your cross section, your theoretical tributary area. So that would just be your trib width from center line to center line to that particular column. For 8-inch thick slab, you can figure that out. But let's say that slab drops down to 10 inches partway through. You need to make sure that P array is increased by either adding tendons at that deeper section or by having a higher P over A through that 8-inch. But you always need to maintain that 125 through any given cross section along the way. But it's a theoretical 125, so it does not account for the pre-compression that's lost from any of that restraint. So, all right, now that we know the tendon configuration, these last steps we're going to blow through a little bit quicker. They're, we talked about balance loading quite a bit already, so we can go through this one a bit faster. And it's not, software does most of the rest of these steps here. So balance loading, we already went through this, so I'm not going to go through it too much more. But again, remember, you're trying to pick up 80% of your dead load. You have those equations. It's P times drape, not P times Z on there. You can set WL squared equal to P times drape. You can put those uplift loads on the slab you apply as an external load. Just refreshing you guys from what we talked about earlier this week and last week. Then you're going to get a moment diagram that's opposite of what your dead load, live load moment diagram looks like. And in general, you want that moment diagram to be countering your dead load moment diagram by about that 60 to 80% range in there. If you go above 100%, you got to really be checking that, because that means you're starting to camber your slab and it's going to be lifting up and you're going to have upwards deflections, and you need to make sure you're thinking about that. So that's roughly where that loose rule of thumb of 60 to 80% comes into play. So tendon layout. So we have this slab. Now we're going to get ready to go into the software and actually start doing it. How are we going to analyze this? What are we actually going to do in the real world? First thing, turn on your dead load only moment diagram, because that's what I keep talking about. We're countering our dead load only moment diagram. So in the software, that's what we're going to do. We're going to turn on moment diagrams for just our dead load only load case on there. And that's really what we're going to see our drape. We're going to try and match our drapes with that. Then you're going to drape your tendons. Always at your edge of slab, you put your tendon at mid height. So if you have an 8-inch slab, you're always exiting your tendon at that 4-inch location, which is different from the pre-stress world, where you'll put tendons offset from your centroid of your cross-section shape, right? In unbonded post-tension, you always exit it at the centroid of your concrete shape. Without doing a bunch of math and getting too far in the weeds, if you were to try and get a little more drape by increasing it, the moments that you're inducing that are unfavorable by, you want more drape than unbonded post tension, right? So if you were to raise that to call it a 6-inch CGS at the end there, you're going to get more drape, which is going to be great. You're going to have more uplift, but you're also getting more negative moment, because now you have a 2-inch eccentricity from your cross section. Those two things really negate themselves if you're to actually get into the weeds of out. So just take my word for it. Always exit those tendons at your centroid, which is going to be mid height. Then drape your tendons, drape them all the way to the low point, and then go to the high points over the columns. What I do is I always keep my high points high, because that's going to be your biggest negative moment region. And so you want that seal up high just for negative fluxure reasons. And then to adjust my drape, I just slowly start bringing my low points up to get within that 60 to 80% mid span. If I'm at full drape and I'm only 30, 40% balanced, then that means I need more tendons. Because we talked about in that equation that, remember, your length, if you look at this W equivalent, we're balancing 80% of our dead load. Our dead load is a constant. 8's obviously a constant. P's your pre-compression. D's your drape that you have, that A value that you're looking at, and your lengths between your column lines is a constant. So that means you can only adjust your drape or your pre-compression to get more balanced loading on there. And if you're maxed out on drape, that means you have to give more pre-compression to it on it. It's also a linear relationship, right? So let's say you run your analysis and you're only balanced 40% of your dead load, and you're trying to get 80% of it, and your drape's only 4 inches. Well, increase that drape to 8 inches, and now you've doubled your drape, you've doubled your balance. Now you're up to that 80% load balancing that you're looking at there. So you got to remember, it's that linear relationship. And when you're running those analysis in the software, keep that in mind, because that actually allows you to do a quick calc on your phone and be like, okay, it's all I need to do is increase by 1 inch, and I should be in that right amount. Versus what I see engineers do is they just kind of increase it a little bit, rerun the analysis, see what it is, and they're just playing a game at that point. And they burn a lot of man hours. So here's an example snip from a piece of software. And the slabs hatch region, we have these 24-inch square columns. Starting from the left to the right, we have a 24.5-foot centerline to centerline bay. And then we have a 12.5-foot, and then we have a 27.75-foot centerline to centerline column spacing on there. And then in the north-south direction, we have 14.5, then we have a 25-foot. So we have left, right, we have a mid-width bay, I'd call it. Then we have a short bay, then we have a long bay. Going north-south, we have a short bay, and then we have a longer bay on that. This is a very common layout that you're going to see. It's never a clean, equal spacing layout that you'd have in there. This is from a podium project that we just kicked out the door a few weeks ago. And so it's a real project and real column layout on there. So the very first thing I do is I put on my dead loads and I say, calculate the self weight of the slab and then add whatever my superimposed dead load is. And then I turn on my moment diagram for the dead load to understand the behavior that I'm trying to counter with those post-tension tendons. And if we're starting to look from the left to the right, we can see that we don't have, this. This region right here is all negative moment because we have this span here and we have this span here pushing down. So because it's all negative moment, if we were to give any drape to our tendons in that region, we're going to be picking up where the slab's already picking up a negative moment. So right off the bat, that tells me I want to take my tendons to a high point. Now I want to keep them high across this area, and then I want to go low with them. What's also kind of interesting about this is, remember, we had a 24-foot span here, we had a 28-foot span here, but this moment, this demand moment's quite a bit higher than this demand moment, which has the longer span. And that's just because this internal one, it's continuous. You have slab to the left, to the right. This one, you have your highest moment, a shorter span. And remember, we're exiting our tendons mid-height here. So we're only going to get a portion of that drape as we go up to the high point, as we would compared to a middle bay. So these end bays, they're always struggling. They're the ones that are always going to control your design. These are the ones that you're typically always going to be putting in negative moment steel. But again, you as the engineer, you're putting in post-tension tendons to counteract your dead load moment. So if you're going to be counteracting your dead load moment, turn on your dead load moment so you understand what you're actually draping and trying to counteract on there. That 60 to 80% rule, that's just that's a loose rule. That's not a code rule. That's more of a guidance on there. So that middle bay, we want that thing to be 0% balanced on there. And that's why we're going to do that no drape in there. What you're looking at now is I'm running my uniform tendons in the left-right direction. And so what you see is these are 3.5. That means that's 3.5 strands. And I'm spacing my tendons at 3 feet in my software, even though in the field I know they're going to be spaced up to 5 feet, but that gives me a tributary width that I can work on. I'm going to figure out how many tendons I need based on 175 psi pre-compression for a 3-foot width on there. And for this particular instance, it was a thicker slab, so it came out to 3.5 tendons. Then I'm going to exit it at, this was a 16-inch deep podium, so I'm exiting at 8 inches. I'm going down to my low point, and then I'm coming up to my high point here. If I go down to this region down here, you can see I'm coming up to my high point of 15 inches, and then I'm keeping my tendon high all the way across this area because I don't want to pick up on that tendon across that short span. If I do any drape right there, I'm picking up in a region that's already in negative flexure. So that's going to hurt us more than it's going to help us. And if you ever did that, you're also picking up in a region where you have a lot of uplift force, but you don't have a lot of concrete above it. So you're picking up, but there's no concrete right there. So even if I need, what's kind of dangerous in these areas is to say, well, I only need 1 or 2 inches. Say you had just a little bit of drape in there. Well, what happens if you do 1 or 2 inches of uplift and you don't have much concrete in the thing, those tendons can actually pop the entire top of that concrete out. And this example, it didn't blow this up. What happened was we walked out on the slab the next day after we stressed, and we noticed a crack, kind of a series of cracks going on here in both directions. Then we started hitting it with a hammer, and it sounded super hollow. And then we're like, all right, we delaminated it. So then we started chipping out the delamination. And what happened in this situation was it was exactly what we're talking about, a different project, but exactly what we're talking about here. There's no drape going across two columns. There's a column here, there's a column here. But the place finishers, when they're standing on this, they stood on these tendons and it actually pushed the tendons down by about 4 inches right there. And then so when we stressed the deck, we're in a negative moment region and we didn't have any concrete right there. And so it just picked up and it delaminated the top of that concrete right there. So how do we repair it? We ended up taking the stress off the tendons. And we put just a little bit of stress on the tendons to straighten them out like a rubber band with them exposed like this. And then we filled kind of this concrete that's got a very high slump below it and refilled in that gap and then re-poured the top of it. After that cured, then we came back and we stressed the tendons and we were good to go. So then let's talk about a region where you're coming from. You have a short span, but you do have a little bit of positive moment, as in this north-south direction right here. What I'm going to do is I'm going to come in at 8 inches right here. Then I'm probably just going to keep it at 8 inches of flat to there, and I'm going to bring it up to a 15-inch height right there. And that's okay. I don't need to have, I'm going to get a little bit of smiley face curvature right here. So I am going to have some load balancing, but even if I kept my tendon straight, this moment's so small that that M over S is probably less than my P over A on there, because that your moment's only what, 70 kip feet there. So in those situations, again, you don't need to be 60 to 80% balanced. That's a general rule of thumb. For more like a bay like this, these you're not going to balance at all or do very little balancing. And the only reason I'm bringing up to my high point is because I know I need my full drape on my backspan, because now I got 360, 400 kip fill moment going on for those long backspans in there. But I'm going to pay attention to this region because it's probably going to be overbalanced, and it's going to come back and tell me I'm 300% balanced, 400% overbalanced. I'm going to look and I'm going to see there's probably not a lot of upwards deflection being 400% overbalanced because it is such a short bay in there, but it's definitely a region that I'm going to spend a little time investigating. Another tricky spot is balconies. So look at this diagram at the very, this little diagram up here. If you have a little short cantilever, you naturally have a pretty big backspan, and just naturally your slab's going to deflect something kind of like this, right? Because of your backspan before you even put PT forces in. And this diagram to the bottom, this is showing a cantilevered balcony, and you're seeing a little bit of, it's very, very tiny, but you're seeing a little bit of uplift that's happening on that balcony simply before we even put in PT tendons, simply because of the backspan that's happening. Now, if I were to introduce PT tendons, I was take a PT tendon and I went from mid depth and I go up to my high point right here. Well, I'm picking up right there. So now I'm making the issue worse, but that way I can get my full drape going back here. So it's a little bit of pick your poison. Sometimes I'll just take these tendons, come in mid depth all the way to right here, and then I'll drape them down. So be careful with balconies about going up to a high point that might start to slope back into the building. What I'll do is I'll try and figure out how much that uplift's going to be. And then if I'm trying to slope out at 2% just for drainage reasons with a balcony on the outside of a building, I might increase that slope a little bit, knowing long-term that balcony is going to slowly pick up. There's been numerous issues that have happened where over time, those balconies actually started to slope back into the building. And then as water hit the balconies, it drained into the door and then underneath the door and into the units themselves. On the left-hand side, this is an analytical model we had on a project. We had these big long bays and we had this cantilever in two directions here and here. And we had, in theory, when we ran our first model, we had 1.75 inches of uplift at our tip out there. And that was from the post-tension forces. So what did we do to mitigate that? We came back and we said, we are not going from, in our first approach, we went from mid-depth up to a high point. We said, we're not going from mid to high. We're just going to keep the tendons mid, and then we're going to drop them down. Same this direction. We're going to keep them mid, drop them down. That helped out quite a bit with that backspan. It's an elastic cross-section all the way through. So the thing's playing teeter-totter. If you screw something over in this bay here on the right, it's going to impact your bay on the left. If you have less load balancing on this bay, and you let this bay really deflect down, it's going to pick up this bay over here. And so a lot of times with post tensioning, you'll be playing with bays over here, or even 2-3 bays down, and all of a sudden something breaks down on the other side. It's because it's playing teeter-totter with itself. So you also got to be thinking about, hey, if I have a bay that's really struggling, maybe my adjacent bay, if it's not struggling as much, I'm not going to do full balancing on there. I'm going to let it kind of pick up that adjacent bay in there. And this is kind of where the art of post-tension design comes into play. And every person in class could do their own design. They could all be right, but they could all be different. For steel, it's pretty easy to tell if you're using like a steel beam going to AISC, and you can tell if you're using the most economical shape on there. So the takeaway is when you're load balancing, turn on those dead load moment diagrams, target balancing that 60 to 80% of your dead load. But that's not a hard and fast rule. In those areas that have either just a little bit of uplift or a little bit of positive moment, or they have no positive moment, it's all negative moment, it's fine to have 0% balance. Or it's fine to be partially overbalanced because you're trying to get up to a high point. You just got to check those stress limits. So that rule only really applies for, these spans here. And you can see this particular span, we're balanced, 80% of our dead load. This one we're balanced 70% of our dead load. This is a super long span going this direction. It looks like we're balanced 82% of our dead load right there. This particular one, we're 100%. So we're trying to get these all within that target region. And then these ones, this one's telling me I'm only 10% dead load balance and my tendons are going flat across it. All right, verify the service level stresses. So now that we've done the balancing, our load balancing is good, then you go check your service level stresses. If your load balancing is within that 60 to 80% and you've thought about all those negative moment regions, chances are all your service stresses are going to work. You might have one failure across your entire slab. So I always say get that load balancing done first before you check service stresses. And that's going to save a lot of man hours on your design in there. We already went through, remember, checking service stresses. It's P over A plus minus your demand load combo at your service and your balanced load combo divided by your S, which is a simple one to do. We talked about using 3000 PSI is a great F prime CI. So that's where you're stressing instead of 5,000, because that usually shaves a couple of days off the construction schedule. And if you start running into those early stress issues when your concrete's still green, it's most likely because you have a podium slab or a big transfer girder. And if you do have that where you're stressing it like a transfer girder that's holding up 30 stories, if you were to stress that entire thing at day one, well, you're picking up 30 stories of air that's not there. So maybe you stress a third of the tendons, go build 10 of those stories, come back, stress another third, go build the next 10, come back, stress the last third, build the final 10 on there. So if you run into those early F prime CI issues, look at potentially doing a stage stressing analysis on there. Moving on, minimum flexure steel. We talked about you have to have some minimum top amount of steel. And again, remember, we've talked about a few times now, but that's really just your minimum amount that you need per the building code for this requirement right here, this 0.0075. You typically don't need it for strength reasons because you have enough PT tendons in there. So all it's doing is providing some crack control because you don't have any bonded steel in there. So it's providing some crack control at your high negative moment region and some magnitude of ductility within the slab itself. We also discussed the only time you need positive flexural steel is if that positive stress goes above 2 square root F prime C. Oops, sorry, this guy right here. And if it goes above 2 square root F prime C, you just have to put in enough steel that's equivalent to the tension the net tension that you'd have in your cross section there. You'll typically, again, see that steel required on these end bays because you have these high moments and you don't have full drape. So it's pretty common to see these end bays in this direction having some amount of minimum steel down there just because you couldn't get that positive flexure tension below that 2 square root F prime C on it. Flexural capacities, again, this is something we've already talked about, but we're going to revisit it again because it's a little bit confusing, is those hyperstatic secondary actions and pre-stressing forces. So if any of you guys ever do get into post-tension design, the first thing you should do when you get to this step is go read one of these tech notes and it took me couple of months to wrap my mind around this idea. It's just so abstract and confusing. But at the 30,000 foot view, it's if you were to stress that slab and those were roller supports instead of columns that actually anchor it down, you would see your slab deflect upwards. And so those columns are holding it downwards. And because they're holding it downwards, you're introducing a secondary force, which is this continuous positive moment that's going across your slab on there. That has a load combo of 1.0 in your, when you go and run your analysis. Remember, at the strength level, you are no longer doing the balanced load approach. You are doing the balanced load approach. Your PT tendons are treated as an external force, right? We looked at how is the external uniform load we put on the slab. At the strength level, it's an internal force, just like a piece of rebar is within your cross section. And so the only external force that you'd be, in theory, applying to your slab at the strength level couch would be the secondary hyperstatic forces. All you have to do as an engineer is know they exist and kind of understand the behavior behind it. The software is going to do this for you. That homework example that I gave you guys, that one goes through and it shows you how to calculate these, where it essentially says your balance moment is equal to P times E plus your secondary moments on there. So you can rearrange the equation to solve for your secondary moments or your hyperstatics. But again, you're never going to actually do this by hand. The software is always going to do it. The only time you're ever going to kind of see it drawn out is that example that we handed out. And for you, your responsibility is just to know it exists. And if you're getting weird behavior in your slab, being able to go and look at those and see, is any of that weird behavior coming from those hyperstatic loads? When you do your analysis for your flexural capacity, again, we've talked about this, but it's very simple. It's just your regular concrete block. Your FMN equals ASFY minus D minus A over 2, right? For your area of steel. The only difference now is you also have an area of pre-stressing that's been introduced into that cross section. So you got to figure out what that APS, FPS number is, multiply by your moment arm right there to the center of your compression block. The difference with calculating your compression block is now you also have to include that APS, FPS force in your analysis, but it's still the same VMN equals ASFY D minus over 2 plus APS, FPS, call it little d times minus A over 2 on there. Right? Again, software is going to do this for you. You don't need to know, aside from doing an example, you don't need to actually know how to do this. You just need to be able to look at this particular example and know that behavior exists. Punching shear, software is going to do this for you again too. So really easy. Your job as an engineer, though, is to figure out, am I using stud rails or am I using drop panels, drop caps? We talked about drop panels and drop caps, where a drop panel from the center line of your column to the edge of that panel, this has to extend at least L over 6 in length. If that does extend at least L over 6 from the center line of your column out, L being your column spacing, then you can use this for additional depth for designing flexure. So if you ever run into flexure issues, all of a sudden, hey, now I have another, this was a podium slab called another 6 inches of depth, which is going to help out my flexural capacities there. Chances are you're not going to need more flexural steel. Sometimes you do. So you're really most of the time just putting in for additional punching shear reinforcement because you've exceeded the max limit that you can do for punching shear. So you give it additional depth right there. Alternatively, you keep this soffit flat and you just put in those stud rails. The stud rails, again, they act just like steel stirrups do. The only difference is that they have a higher allowable stress limit in ACI, which is 8 square root F prime C. Then rebar has a 6 square root as a max stress that you're allowed to do for punching shear. So they do give you a little more boost in your punching shear calculations. With them being, with post tension being such thin slabs, lots of times your controlling element is that punching shear behavior at your columns. actually calculating punching shear with pre-stress and all that, it's a very, very complex, complicated calculation. There's a whole group in ACI that all they do is nerd out about this stuff, and even them, they don't fully understand what's going on with punching shear. It's concrete, right? You can only understand it to so much. That said group in 31819 decided to do this new code provision where they said anytime you have a slab that's greater than 10 inches, you have to use this shape factor and you have to reduce your capacity that you get for punching shear resistance out of it. And what they're really trying to say was this is a smooth shank and you have an anchor head here and you have an anchor head here. So when you have a really deep slab, if you're punching cracks coming across your cross section like that, you don't have much bond, you don't have anything bonded in this area because that's smooth. So because if it's greater than 10 inches, we want to reduce the factors that are going on there. The folks at PTI are pushing very hard to get rid of that code provision. They think it's a bunch of BS. I think the guys who wrote it just wrote it to get their name in ACI for ego reasons. So there is a huge fight going on right now, which is pretty interesting to watch. And they're pushing really hard for ACI to pull back on this in future code provisions, at least with post-tension slabs, to say that shape factor doesn't exist. You don't need to take a reduction on it. ACI kind of hinted at, well, they're so vague about it. It pisses me off because these codes are they're supposed to be the explicit thing that everybody follows, and they give you this vague language that you can't understand. And they kind of say, well, it helps if you piggyback your studs, which is this what you're seeing right here, where you're welding on top of it, there and there. It helps you out by piggybacking because now you do have some bond along that length, but it doesn't explicitly tell you by piggybacking, you don't have to take that reduction in punching shear. And where this really kills us is on these podiums that are 12, 14, 16, 18 inches thick. Also now podiums are starting to grow by 2-4 inches in thickness because of this requirement that, again, punching shears are a controlling thing. They introduced this law that nobody really understands. So hopefully by the next code cycle, that'll be pushed back. But this is a relatively new thing in the world of punching shear that has a lot of people really upset. Long-term deflections and vibrations, we haven't really touched too much on this topic yet, but when you analyze these slabs, again, the software is going to do it for you. You just need to understand how to do the input, but it does a nonlinear time step deflection analysis, and it runs through this deflection that you're going to see over time. And I have a snip of exactly how I set it up in my software. And so it'll run an analysis when you first stress the slabs and you have more PT forces in there. That's going to run analysis with the building complete full live load on there. Then it's going to sustain. Remember, we talked about sustaining a percentage of our live load, 10%, 20%, whatever it is. It's going to sustain that load for, in my calc, it's 5,500 days. And it's going to go through a bunch of inelastic creep on there. And then I'm going to look at it again, and I got these other two, call them load cases set up, where I can go back and I can see how much long-term deflection am I going to get out of this slab. ACI has limits out there where they say, use these, they have two approaches. One, they say on a regular mild slab, don't exceed the span to depth ratio so you don't have these issues. Another, they have some base coefficients that you can multiply times your elastic deflection to get your inelastic deflection. Or they say you can go do a crazy advanced analysis and it does all these calculations. They'll tell you how much inelastic deflection you have. And this doesn't matter whether you have a mild slab or a PT slab. You have to either follow the ACI approach with those coefficients. And those coefficients are extremely conservative and they're going to show you your deflection's way worse than it's probably going to be. Or you run this crazy nonlinear time history analysis. Well, this nonlinear time history analysis is kind of based on ACI 209, which is this prediction of creep, shrinkage, and temperature effects in concrete structures document. And the first thing this document says is, we really don't know what's going on. It's very variable. This is our best guess at it. So you should use your engineering judgment. So what I tell people is, if you have something that's extremely deflection sensitive, like a facade around your building, a curtain wall or something, and the supplier tells you your slab can only deflect 1/2 of an inch. And then you go and you run your analysis, and your analysis comes back and tells you, you do this crazy nonlinear analysis. It takes 30 minutes for the software to run it. You're feeling smart. It comes back and tells you have 0.48 inches of deflection. And you're like, well, that's less than 0.5. green's good, right? Well, we always say in software, just because it's red doesn't mean it's failing, but also just because it's green doesn't mean it's passing. That's one of those situations I'd say just because the software is telling me it's less than that half of an inch doesn't necessarily mean it's good because it's not, we don't know what's going on. So because I'm so close to my deflection limit, I'm probably going to add a little beam into the slab, or I might do a turned up wall that's 6 inches wide and do it, call it 4 feet tall, a little knee wall on the edge of my building. Now I've introduced a very stiff element that's going to control my deflection, and now I don't have an issue. So if I'm anywhere even close to my deflection limit on the edge, I'll usually add a stiffening element in there. However, if I run that deflection analysis and it says, okay, you have a 1/4 of an inch deflection, I know it's a 1/2 inch, okay, I got plenty of wiggle room no matter what happens out there on it. Okay, so drawings and specs. So now we're running through this. How do we specify things on the drawings and where do we know where to go? Again, PTI's got a lot of resources online. You can go to one of their tech notes and it says, do you specify the final effective force or the number of tendons? If you specify the number of tendons, then you have to say, I assumed every tendon has 26.8 kips of final effective force on there. I say specify the final effective force. And so this one is, it's 429 kips. If I were to go 429 divided by 26.8, that comes out to 16 tendons. So when I was running my analysis on my banded layout, I already knew that it was going to be a clean number, and I kind of set the banded 10 lines up for success. In the uniform direction, I just said, okay, you got to give me 31.3 kips per lineal foot. I don't care how you space those tendons. I just care at the end of the day that I have 31 point kips of pre-compression per foot of length on there. And then you simply, again, you specify your high points, your low points. This is that same slab. You can see where I'm keeping my uniform tendons high going all the way across, then down to a low point right there. You specify those. The PT supplier actually goes and figures out the chair heights. We talked about the anchorage zones. The PT supplier is responsible for the anchorage right behind the PT head, but you as the engineer are responsible for this general anchorage zone and making sure that you have some sort of reinforcement in here to negate that bursting. So that gets missed a lot. And all you guys have to remember is if it's more than a banded tendon set, like stack tendons or a beam, I need to be designing that region in there. If I'm not, I need to be explicitly delegating that to the PT supplier. So that gives you a little bit of guidance through this technical note in here on how to put the drawings together. What about the specifications? The easiest thing to do is just use the specs that somebody else has already done, which is PTI's created these specifications. Some people write out these long specs. They have them in their spec book. All I do is I have one line in my journal notes and I say reference PTI M10.2-17. There's your specs. There's no reason for me to just copy and paste them and put it in there when that document already exists. I could do it to make it look like I have more information, I guess, but really there's just no reason for it. So I simply just say use that document and keep one of these documents on hand. So if you're doing post-tension design and you're the first person in your office to ever do one and you got to put the specs together, all you do is you just go to this reference document there. So construction administration, once you get into the field side of it, you know, I always tell people all those hours that you've now saved in design because you're following these steps, and if you follow these steps, you're going to be more efficient in design. Burn a few of those hours out in the field, really understanding what's going on, and you'll see those issues. We saw this picture on the left before, but you'll see those issues where, hey, I'm trying to dump 20 plus tendons into this beam. It's just not happening. Don't do that. You learn not to do that. Slab steps. What you're looking at here, this is a hanging form. So our concrete slab is going to come over, and that's going to step down, I don't know, 8 inches or so. And then it's going to come over right there. And so that's how you form up one of those steps in these podium slabs. So you're looking at a hanging form in here, and we're running our tendons through that hanging form. Well, what happens a lot, and you can see it in this circle here, the natural drape of those tendons will often be touching that form there. So sometimes you actually need to lower these tendons a little bit lower at these slab steps to not be touching where this inside face of that slab step. Another one is I talked about you need that 125 P/8 at every cross section along the way. Well, say you had 125 at this thinner slab and now you have this thicker slab down here. Well, this particular engineer added a bunch of PT tendons in the thicker region. And you can see these heads are stressing out underneath the formwork. What's really challenging is you have all this formwork built up under there. Yeah, you have to stress the tendons before you can strip the formwork, but you got to strip the formwork to get to the tendon heads. So there's a little bit of a chicken and egg situation set up right there. So it's these type of things that you'll see when you go spend some time out in the field. And you just can't capture those unless you spend time in the field really looking at the issues they're having. The next big thing that comes up in CA a lot is measuring those tendons. Per that specification that I just referenced you guys to, it says your theoretical tendon elongation needs to be within 7% of your actual elongation on there. And that's a backup check to the gauge pressure that you guys used. Well, again, there's a tech note out there about this, but when you have short tendon pulls, called 20 feet, you're going to reach that, 1/8 of an inch is going to be the difference between being within 7%. So if you have a short tendon pull, I usually tell them, hey, if the tendon's 20, 25 feet long, I keep it at 3/8 of an inch for your allowable in there. And then again, I say 7% is the rule, but just because you hit 7% or didn't hit 7%, I don't want you to go re-pull those tendons. That's pretty dangerous. I'm going to use my engineering judgment to figure out if it's still good or not good. And if it's not, the only reason I'm going to have them re-pull the tendon is to try and verify how much force was on. I'm never going to do it to try and get within that 7%. Typically, you're out of spec because there's just sloppy marking on your tendon elongation. So from that standpoint, there's a technical note out there to give you some guidance. So when you look back on this document here, if you guys ever go do PT design in the real world, after you wrap your mind around the first couple presentations we did, which was this is what these PT slabs look like and the fundamentals of the design, use these 12 steps. If you follow these steps, you'll set yourself up for success to not be doing iteration over iteration, and get that slab geometry right at the very beginning. Get your restraint shortening figured out. Then lay out your tendons. Once you do that, everything else just kind of falls into place. And then if you balance those loads properly, I can almost guarantee you all your service level stresses are going to check out, your capacities are going to check out, the software is going to design the punching shear, your long-term deflection is going to check out, then your drawings and your specs, I showed you guys the documents to reference. So this slide right here should serve as your design guide for doing it out in the real world. And then if you need more information at the end of this presentation that you guys have, I've given a ton of different resource documents. So this will give you the confidence of, hey, I'm following stuff. And most of these are peer reviewed too. You have the post-tension manual. You have 2 different textbooks out there on post-tension concrete design. You have these design guides for post-tension buildings and for restraint to shortening. You have these specifications that we talked about that you can fall back and reference. You also have on PTI's website, you have frequently asked questions where they ask questions about elongations. They ask it about backup bars, field issues, all those. So you can go look at those FAQs. You can go look at tech notes that they've written for different things like short tendon elongations, those secondary moments, hyperstatics. There's a lot of information out there. We wrote one on dual banded post-tension. And then there's these webinars that we've been doing for the last 2 years at PTI, where every month there's a webinar that's something new coming out on there to kind of keep you up to speed. So all that being said, you guys should at this point have enough to BS, if you will, or just trip over yourselves if you're ever to do PT design. You have the fundamentals. You have more than any other engineer graduating from a grad program. I'll tell you that much right now walking out. And this is the same exact training that we use to train our engineers to go from the beginning. So save this stuff, keep it. If you do post-tension design, you'll be referencing it, and you guys should be set up for success.
Cool. Well, thanks a lot, Kyle. This is, like you said, it's super helpful for you to do this for us, because I would not know how to start this process. So that's awesome that you can show us this. So and I think I said for real world example, Elias, which we don't know at this point, he started doing PT design. He was one of the first in his office, and then he just grabbed this stuff from Kyle and just started going through it. It's like, this is awesome. So yeah. Hopefully get you started. And you can always call Kyle too. You guys call Kyle.
You sure can.
Yeah. I think Kyle looks to hire people sometimes too, right? Is that a true statement, Kyle?
I sure do.
Okay, yeah. But none of these guys. But fine.
They came up under you. They're pretty smart, right?
Yeah, that's right.
Yeah, no, we're always interested in hiring. We're growing. You know, we do. We have remote employees. We have employees over in Poland. We have kind of employees all over, so we're not stuck on being in a certain office. And we do projects all throughout the U.S. We don't do a lot of stuff in Montana, just because most stuff we do is either bigger or just not Montana. I'm just not a wood engineer,
Sure.
but
Yeah.
because why?
Yeah. Well, cool. Thanks a lot, Kyle. Thanks for your time and doing this stuff. So,
All right, guys.
we can help you out at all. So,
Yep, good luck with the rest of the semester. I enjoyed it.
Yep.
Talk to you later.
Yep. Thanks, Kyle.